So as he said, I'll be talking about function secret sharing. This is a joint work together with Niv Gilboa right here and Yuval Ishai. And will be appearing in the upcoming Eurocrypt. So let me start it out by one of our old friends here, a standard additive secret sharing scheme. Okay, so we're thinking in this setting of some sort of abelian group, and we have some secret, and we want to split this secret into different parts, such that each of the individual parts hides the original secret. But if you add the shares together, this is the reconstruction property that we require, that they add to the secret itself. Kind of just to put you in the right field here, for this whole talk, I'll be talking about passive adversaries, so forget about robustness or anything. These are the properties that we're interested in. Okay, so today is about function secret sharing. Okay, so we can think about these functions as, say here, from n-bit inputs to elements of a group. So in some sense, this function is characterizing 2 to the n different secret inputs. Secret values. And the question is, since we have some sort of compact, nice representation of these secrets via the function itself, can we also secret share these in a more efficient way collectively? That is, so we want to think about secret sharing the function itself. Okay? So for example, say that we take this function, we want to split this into 2 different parts, such that each individual function hides the original. But now, given kind of my share, this f0, later on I'll also refer to these as keys for this particular function. The given I share, f sub I, for any input that comes along, I can evaluate this on my share, and you can evaluate it on yours. And we have the property that these values will exactly be an additive secret sharing of the evaluation f of x. What we're really interested in is where we have some sort of efficiency property. So for example, the size, the complexity of this procedure is comparable to f itself. So one note right off the bat is that if you want to hope for some sort of statistical or perfect security, you're unfortunately going to be kind of stuck. That you're going to need the size of these things to scale with the truth table of the function, so this 2 to the n here. Whereas if you're okay with computational security, and just that efficient adversary, given, say, one of these pieces, can't distinguish whether this came from some f or f prime, then you can hope to do much better. So that's the focus of this work. We'll be looking at computationally hiding. Mm-hmm. Yes. Yeah, so in fact, we're going to be considering settings in a lot of the applications and things where x will be public, but we want to hide as the function itself. Good. Okay, so a couple comparisons. Maybe this sounds a little bit similar to the notion, if you've heard of threshold cryptography. So this, back at, in the 90s, people considered a setting where you have some sort of secret functionality, say like a specific cryptographic functionality, for example, a signing algorithm with respect to some key. And they split this function into pieces. So I give you one share of this signing functionality and you one share of it, such that given only one share, for example, I can't generate a signature on its own, but if you combine our outputs, they can generate. So the difference here is that in these works in threshold cryptography, they have kind of the ability that they can choose nice functions that have good algebraic structure, for example, some sort of homomorphic property for this combination. And in this work, we want to look at more general functionalities. In particular, so this project was inspired by a recent work last year of Gilboa and Ishai that look at the specific function class where the f's are point functions. So in fact, they're equal to 0 except for a single hidden input. So effectively, this means I want to generate 2 efficient pieces of this function that agree on every single input except for one hidden input. All right, so there's a little bit of a few slides here. I want to talk a little bit about some applications of why this is a cool notion. So as a warm-up application, this is in fact something that was implied already with the distributed point functions. Whenever I say this, this is referring to when the function class is the class of point functions. And that's a 2-server private information retrieval. Okay? So we have a setting where two servers have some database, and we want to, as some clients say, I want to access some item of the database, but without revealing to the servers which item I want to access. Okay, so say that I is our secret target location. How we can do this is, so consider the point function that's equal to 1 exactly on input I, but equal to 0 everywhere else. Now, if you can secret share this function and communicate, so give each of the servers gets one piece of this function. On this side, so there's some computation that's going to be done with respect to this piece, which corresponds to essentially evaluating for each of the different values in the database. I'm going to evaluate my share FA on this index, say. And when I do all these evaluations, I'll add them together. So evaluate, use this as a coefficient, and take this linear combination. So what's the point? The point is that, so do this computation and send it back. And the point is exactly because of the reconstruction property that everything here is going to cancel out. I'll have exactly the same coefficient here as is here for everywhere except for position I. So for simplicity, think about, say, characteristic 2, where adding is the same as subtraction. Okay? But on the other hand, by the secrecy property, since each server only sees one piece of this function, he learns nothing about the index I. And the benefit here is that the communication required is actually quite small, so comparable to the size of the DPF, the point function, which can be described small, and the value itself. All right, so here I want to go today beyond point functions, and I want to say that in terms of the applications, once you can start supporting more expressive, more rich function classes, you can extend these applications. So for example, consider again with this two-server setting, but I want to do something more than just retrieve a single element. For example, maybe I want to do some sort of counting queries, counting how many of the data values satisfy some predicate. Or say I even want to do a recovery, so I want to learn the data items that satisfy this predicate. And you can kind of capture these in different settings in terms of what, for example, the group is or what the function should be. And one thing I want to emphasize here, so in the previous example, the function was being evaluated on the index, that I just wanted index I and nothing else. But you can, in the same way, you can also apply these functions to any public data, so the data itself in these examples. So let me give another explicit example here. So say I have some more elaborate counting query with some predicate and more information in the database. And the point is I can do essentially the same approach. Okay, so I have now some more expressive function. I'll secret share it, send each server his respective share. And now the evaluation, instead of evaluating just on, say, the index, you'll just evaluate on each of the different parts of the data. Send the shares back. And so for this example with the counting queries, you'll get, when you add the two pieces together, you'll get a contribution only for those values that had a 1, versus all the ones that have a 0 are going to go away. And pushing even a little bit further beyond, I don't want to focus on this, but using kind of standard techniques in linear sketching, you can also do this to recover the values themselves instead of just a count of how many things were satisfying. And here note that the information that you send back is actually going to be a vector. So say that you know you want to be able to recover m entries, the thing that you get back will be, say, m dimensions. So even one last type of application, which I think is pretty cool actually, is the point that, so all of these have been of a regime that somebody owns the data and the data is not changing and I want to access some information about it. But you can actually use these tools even to update the data itself if it's held in a secret shared fashion. So some kind of incremental secret sharing. As an example, think about something like private cumulative statistics. So suppose that I want to keep track of how many hits particular websites get. So one way you could do this is have some sort of central area. And every time somebody accesses a website, they send this information gets registered. Say this IP was looking at this particular website. Okay, but this has sort of an issue with privacy. You know, sometimes I don't want associated with me things potentially that are looked up. So we want to remove this central guy who has these links. Instead, consider splitting this across 2 different servers that have a secret sharing of the database. So nobody actually gets to see exactly the data in the clear, but they just have some additive secret sharing. And now, each time somebody accesses a website in this example, they can consider, say the point function that's equal to 1 exactly on input Google and equal to 0 everywhere else. Split it into pieces and send to the servers their shares of this function. Now, each of the servers will update the database in essentially the analogous way as computing for the private information retrieval, except that now instead of just reading, basically you'll update each of these values by, so this was the original value of whatever the website is, so Google, WebMD, so on. And now you replace it with what you had before, plus the share of this function evaluated on that value. So the point is that everywhere except for Google, these contributions that you've added in are going to cancel out. And on Google, it will exactly increment by 1. Okay. So one thing that I want to mention, so in fact, you can actually consider different schemes, for example, with fully homomorphic encryption. One benefit with those is that you can consider a single server case. But if you actually want to implement these things, the results that we get from, say, function secret sharing are much more effective and efficient for a couple different reasons. So even right off the bat, the assumptions are much lighter. We'll be talking today mostly about things based on one-way functions, as opposed to heavier things with fully homomorphic encryption. The computation and also the communication actually is going to be lower in our settings as well. Because instead of needing to do things like heavy homomorphic evaluations or sending things like ciphertext encryptions of bits, you're just going to send the bits themselves, and you can do the computations directly. So I've been talking about, I sort of took for granted that we're interested in additive secret sharing. But something to point out actually is that you could consider more complex or more expressive reconstructions. But I want to argue that you shouldn't. Not that you shouldn't, but actually that by considering these additive reconstruction, that in fact this is why we're able to get a lot of the applications. So here when I'm talking about reconstruction, just to be clear, I mean once you have your share, you evaluated these, I'll refer to these sometimes as output shares, but how do you take these and convert these to the evaluation f of x? So in our particular applications, we wanted these output shares to be short, compact. We want them to have some sort of function privacy. So by seeing y0 of x and y1 of x, I don't want to suddenly learn what f was to begin with. And we really made use, particularly in these peer type applications, of the fact that we had some kind of linearity, which allowed us to compress the results, say that the servers were computing, and send it over in short form. But there has actually, so there are a lot of interesting things that you can do. I want to call out here to a work of Boyle et al. Back in 2000, which has a very similar flavor in terms of the goal of the construction, not the constructions, referred to as computing functions of a shared secret. But here, so they consider settings with more complex reconstructions, including things, so with interaction, but also without interaction. Okay. Good. So halfway through the talk, I can tell you what do we actually do. So here's kind of a map of the world, right? So let me emphasize at this point that when you talk about a construction, a function secret sharing construction, this is with respect to some function class. So it'll be able to support functions in this class for correctness, and also the security is with respect to a class that I can't distinguish if it was some f or f prime within this class. So down here is corresponding to more of the weaker lightweight things, and up at the top is sort of everything you could hope for on the circuit zone. Okay, so our first contribution is an improved this distributed point function construction from one-way functions, improving with respect to the Gilboa-Shai work from last year. Can you see this? It's a little hard, actually. So the improvement here is with respect to the efficiency. Say the key size, for example. In the original scheme, it was n to the log base 2, 3, and we get this down to linear. We give constructions, so I've been talking about the two-party case, but you can actually consider this for lots of different parties, where each party gets some share of the function. And you can consider different subsets as being corrupted or not. So we provide the first non-trivial solutions for distributed point functions with multiple parties. As you can see, there's still a lot of work that can be done here, and these are still pretty big keys, but there's some fun techniques there. We show a relation that as soon as the function class that's supported is sufficiently rich, which in particular includes point functions, the pieces, these F0, the share of the functions themselves, are actually pseudo-random functions. And we also give a bunch of general transformations. So some of them are, on their own, seem kind of straightforward, but it's pretty cool to see how they build on top of each other. So by general transformations, I mean, say if I give you an FSS scheme, function secret sharing scheme for some class F and for some class G, that you can combine these and get some more expressive function class. So for example, some of these transformations make a lot of use of the linearity. And also you can do things, this is kind of jumping the gun, but you can do some fun things like if you pre-compose with functions, that's also okay. But I'm not going to clarify that statement. So combining these things together, building in particular on top of the DPF and some of the general transformations, we give constructions based on one-way functions so interval functions. We get two constructions, actually, one that comes with these nice parameters and another one that's black box from any DPF. You can do multi-keyword search, you can do NC0 and things of this kind. Okay, so I've drawn this line here. Why? Because interestingly enough, as soon as you jump up to AC0, we provide evidence that it appears like these are going to require somewhat heavy cryptographic tools. So I'll clarify that a little bit, but not now. So what else? We also show that if you have function secret sharing for NC1, you can use this in Bootstrap together with fully homomorphic encryption to get function secret sharing for all P/poly. And at the very top, we give a general construction for P/poly based on obfuscation. So you can do either, there's a somewhat simpler construction based on virtual black box, but with an amount more work, you can actually get this from sub-exponential secure indistinguishability obfuscation. So here's the map. And these are the different results. And just kind of, what's sort of the takeaway? There's a lot of bits and pieces here about the complexity of all these functions. So with respect to, say, these worlds, the many worlds of Impagliazzo, in some sense, can kind of collapse these into pre-2010 script. And we're kind of looking beyond that. So by ultracrypt, I mean things like fully homomorphic encryption and reusable garbled circuits. And even looking even further, we can consider some kind of megacrypt, which is in the world the regime of obfuscation. And the takeaway, the point here is that it seems like these constructions, so things like point functions and NC0, are down the bottom. And in fact, we can get them even with one-way functions. And all these other guys are somewhere in this regime that we show that we can get it from obfuscation, but it appears, it looks like it's going to require something above the green. So I had wonderful slides for those that I'm not going to cover. Basically what we do is we show that if you have function secret sharing for these, then that implies a kind of nice multi-party computation protocol with low online communication complexity. which is, yeah, we only know how to achieve that now based on fully homomorphic encryption or reusable Garfield circuits. It's sort of this reusability that has the good property. So I think as soon as you want to go information theoretic, I think you run into these bounds that you need enough secrecy that I don't think you'll be able to compress. I see. So that's interesting, actually. That's possible. Yeah, that's possible. Okay. Good. So, yeah, I made slides for all sorts of different things and continually kept cutting out and out. So what made the cut a bit, maybe, is the construction down here of the improved distributed point function. So this is what I want to tell you about today. So let us begin. Okay, so just kind of a refresh. What's the goal here? Remember, we're looking at the function class that corresponds to all the point functions, and we want to be able to generate keys for two parties. Essentially, this is some function that, in fact, we know is going to have to look like a pseudorandom function. That's sort of an aside. And we want them to agree on all points except for one secret point. Okay, so here's a high-level view of what our construction is going to look like. We're going to give each of the parties some key. Again, the key I'm using interchangeably with the f sub a. This is just my share of the function. And this key is somehow going to define a binary tree. So each individually, on each of these nodes, this is going to have, for the party defined by the key, will be some random looking value. And we'll have the property that all the values across these two parties are going to be equal, except for down this special path. So here, down the leaves correspond to inputs, and this key, whenever you want to evaluate on a particular input, will be done by traversing down the path. So note that this, if we could achieve this, this would give us what we want. So for example, if we evaluate on some input that's not the special input, we'll get two values that are equal to each other, so they'll cancel out. And if you evaluate down exactly on this special input, you'll get some value that'll be different. And it'll be the case that basically, as long as we can get them to be not equal, and that the difference is some random unknown value, you can always do kind of a multiplicative offset to direct it to wherever you want. Okay. So how do we achieve this is sort of the question with the small key. So this is what the structure is going to look like, starting at the very top, and we'll kind of describe how to go from level to level. At the very beginning, so this is part of the key that each party is given. This is the one party and this is the other. It's going to correspond to these particular values. So these short guys, the t's, will be a single bit, and the longer ones are going to correspond to seed of the pseudorandom generator. Remember, we rely on PRGs. So some lambda bits. Okay, and during the evaluation, so we'll start with these values, and as we go through stepping down evaluating on an input, we want to somehow generate 4 tuples of this form for each level of the tree. And I don't want to carry around all this notation. This is pretty heavy here. So what are the things to keep in mind? So here I've got this L. This represents, I'm going to use this part of my information to go to the left side. And on the R will be going to the right. And here, remember that everything that I'm looking at here just on one side looks totally random. But we have the property that if you look across the two parties, whenever I do something in this black color, this means that it's the same value across the parties. And when I do blue versus red, these are going to be different values. And also, I don't want to, so whenever I do a short thing, this is going to be 1 bit, and whenever I do a long thing, it's going to be this lambda bit. For example, like this. Okay, so the goal, again, is to give some way of going from one level to the next level, I+1, preserving the path structure. What do I mean by this? I mean, here we had this black and blue corresponding to black and blue. Now when we go to the next level, I'm using this key to generate the tuple over here. And I want these to both be black and black when you go left or right from this node. And here it's going to be, so there's blue here, but now blue and black. Good. We got the colors. Nobody's colorblind, right? That would be not the best. Okay. So I told you that this is going to be a seed for a PRG. So maybe you can be thinking in your mind that one thing we might want to do with this is apply a pseudorandom generator to it. Okay? So by the way, this is describing how are we doing this step going from one level to the next. So expand this out. It'll be some longer string. Parse this in terms of the same format as the for tuple before. And the same over here if you wanted to go to the right. So note that if this guy starts black, that is that they're equal across parties, the output of the PRG is also going to be black. And same if you start different, where these are going to be different and uncorrelated, the outputs will also be. So this is partly good, but what we wanted, remember, was this black, black, blue, black. So this exactly corresponds to the point where as soon as I depart from the path, this colored path in the tree, I want my values now to agree. So in order to force this at this level, we're going to use a technique that's actually inspired also by the Gilbo-Ishai work, referring to these correction words. Okay, so one question is, so think about what is the difference right now between this and the red guy? It would be the sum of these. What is the target, what is the difference that we want? We want it to be that the second half is going to agree, so we have sort of a 0 here, and the first half is some other garbage. Okay, so now take the sum of all of these things, and this is going to be some sort of correction word that we want to add in. But note that we can't just directly add it in here, because if we added it in the other sides, in the other parts, then we'd lose the agreement. So also, by the way, I want to emphasize that since, as the blue guy, I know nothing about the red guy's string. I don't know what this is. It looks random given my view. So this string is also going to be random. This is sort of acting as a mask. Okay? So what are we actually going to do? We're going to put this into 2 different pieces and include these pieces as part of the key. So, by the way, I've been ignoring up until now this extra bit, and this is exactly where that bit is going to come in. The bit is going to tell you which of the 2 pieces do you add in each spot. Okay, so again, from the beginning, so we expanded this guy as a PRG. Now, say that this bit is 1. To do the next step, I'm going to take the correction word, the sub 1, and add it in to this part. Since over here is a 0, I'll take the 0th one and add that in here. And what's the point? The point is that the other party, remember, since these, the black ones all agreed, the bit also agreed, so he's going to add in exactly the same vector here. Whereas over here, this blue and red bits were in disagreement, and so we'll add in the 2 different parts that add to what we want. And just kind of driving this point home, now we have the property that the left side completely agrees, and the right side, based on the choice of these correction words here, is going to give us the correct sum. Namely, the second half will agree across the 2 parties, and the first half will still be this uncorrelated not equal that we want. Yes, yep. Mm-hmm. So in fact, exactly, what will the structure of the key look like? Well, we have these initial guys that we started with, and exactly for every level of the tree, we're going to have a distinct pair of correction words. But something to note is that we only need 1 pair per level, and it's exactly the same across the 2 parties. So I thought it was kind of interesting that with all of these bits and pieces, the only thing that's different between the 2 parties' keys is say, just this one piece right here. In terms of key size, when I say linear, we're talking about actually reasonable constants here. The total key size is just going to be essentially 2, so 2 copies of everything. The 1 bit here for lambda times n for n is the depth of the tree. Okay. Yeah? So you can do that exactly with the correction word. I didn't describe it, just a second. Where did I put that? Oops, not yet. Good, so whenever the target difference here, this is going to be just randomness, and this is going to be 1 here, saying that I want the difference to be, I want them to be different. Good. All right. Cool, so that is the construction, and I want to just give a little bit of a conclusion here. So again, I was talking about function secret sharing. I think that there's a lot of really cool questions and directions that are not yet explored. So kind of 3 different categories I think of. One is more constructions. And actually, there's a lot of different, oh, sorry, I'm skipping ahead. Okay, these are what we did do, so don't do these problems. Or you could try to get cheaper. You could potentially get the constant down. Okay, so what we achieved, we gave a cheaper construction of the distributed point functions with linear key size. So blue is stuff that I didn't get time to talk about. We give, so this non-trivial DPF construction for many parties. We have a lot of these just different general transformations, which can kind of be pieced together in nice ways. And also we give this construction for general FSS, for any P/poly, from sub-exponentially hard indistinguishability obfuscation. In terms of relations to other primitives, oh yeah, so this should be blue. This is a last-minute change. I didn't talk about either of these, but we give these barriers for AC0 and up. And again, what do we do? Each of those are kind of the form that if you have function secret sharing for AC0 or for more expressive function classes, this gives you something that we currently only know how to achieve based on things like fully homomorphic encryption for AC0 or reusable garbled circuits for AC0, and that scales up as you go up. And we also show that the key functions themselves, once you have sufficiently rich function class, are pseudo-random functions. Now for the future directions. So what I've written here is just kind of some of the maybe simplest versions of things that we still don't know that seem like you should be able to do. So for example, even just aiming for AC0 based on some of these things, like say I'm okay with using reusable garbled circuits or fully homomorphic encryption or learning with errors, can you get these constructions? There's a lot of work still, a lot of improvement that can be made for the multi-party case. I think that that's actually quite interesting. In terms of lower bounds, so we give these evidence, but maybe you can actually show firm lower bounds, even for lower hanging things. Things like public key encryption it's not even clear at this point if that's required. I mean, yep. And in terms of applications, so where else can we put these things in? Are there potential applications in things like obfuscation or other regimes? So with that, I'll conclude. Thank you.